NASA's newest mission. So, thank you very much.
Great, thank you very much. This might be a little bit of a change of pace, but since I was out here anyway, I asked Giovanna and Greg if they could make a little bit of room on the agenda for me, and they did, which I greatly appreciate. So the reason that Giovanna referred to this as NASA's newest mission is because, as many of you know, we've been working on the Europa mission for quite some time now, but we're done trying to get it started. As of about a month ago, NASA finally gave the full green light to move this mission into implementation. So I'll be talking about that a little bit today. Given that, I thought it might be of interest to you guys because that means that things are going to start moving kind of quickly in this area. So, Europa. Europa first came to our attention prominently in the 1990s when the Galileo mission performed its handful of flybys. And the evidence began to build very persuasively that this was a pretty unique object that was covered with a global liquid water ocean, capped with an ice layer of unknown thickness. In the intervening time, given the limited data sets that we have hypothesized a lot of things about Europa. We think we know various things to various levels of confidence, but we don't know a lot of things, which is why we need a mission there. We think that Europa has all the ingredients for life. We think that it has the necessary energy source to keep that life going. We think that it has the necessary chemistry and nutrients to provide food for any life that could evolve. We think it's been a stable enough environment for billions of years, long enough to provide a very conducive environment for life as well. But these are all things that we think we know, like I said, to varying levels of confidence. What we're ready to do at this point, after spending a couple of days crunching these numbers, is go forward with a mission that not only will pose questions like this, but must be able to answer them, to address these key hypotheses about what could be the most conducive environment for life beyond Earth in our solar system. And not life a billion or 2 billion years ago, life today. So the big question for Europa then is not, is there an ocean? It's not, what's the brown stuff? The big question is it habitable? As I've explained to various people at various levels of management, it's very difficult to jump right to the is there life question, because we don't have a handy-dandy life detector. In fact, we don't even have consensus in the astrobiology community as to what you would measure in order to conclude with confidence that there's life. But what we do know how to do is assess habitability. We've done it. We continue to do it on Mars. As Chris alluded to a few minutes ago, it looks like Ceres might be worth an extra look in this area as well. So we have a lot of experience assessing habitability. So it always makes more sense before you jump to the hard question that costs a lot of money to answer, is there life? You first ask the easier question, is it habitable? That's what we're going after with the Europa mission. And as with all big questions, it's relatively easy to pose it. But the difficulties arise when you get down into the implementation. So for Europa, I break down that big question of is it habitable into nice, simple questions that we need to address. First, how deep and salty is that ocean, that global ocean on Europa? We have proven ways of going about answering this through magnetometry and gravity measurements. We've done it on other missions like Grail and Grace and Galileo. How thick is that ice shell? This is an important question because if that ice shell is 100 kilometers thick, it presents a pretty formidable obstacle to exchanging things between the ocean and the surface of Europa. But we also have experience with different instrument measurements for addressing that question. How active is that ice shell? Whether that ice shell is 100 kilometers thick or 50 meters thick, which, to be clear, nobody thinks is the case, what really matters is how active is it? What's the geology there? Because if that ice shell is active and it's acting as a conveyor belt, then we do have a process by which the stuff on the surface, which is a radiation processed, provides a lot of oxidants, can then get down into the ocean and provide some of the necessary things that life might need. In addition, it implies that there could be stuff from the ocean that is being brought up to the surface, which is a huge benefit because it is a lot easier to sample something that's sitting on a surface as opposed to something that's buried beneath tens of kilometers of ice. And then, what's the brown stuff? As those of you who have seen pictures of Europa before, one of the key questions we have is, what is that reddish-brown gunk? And this is interesting because it appears to be uniquely situated among the youngest areas on Europa's crust. It looks like it could be stuff that's erupting onto the surface from beneath. That could be the samples from the European Ocean that we're so keen to get our hands on. And then the wild card question that's come up recently, what's in the plumes? A couple years ago, the Hubble Space Telescope made a detection of essentially water erupting from the South Pole of Europa. That has tremendous implications for not just the science, but the exploration, because it suggests that we may not even have to land in order to try to access that sample from the ocean. If those plumes are actually connected to the ocean, it means that the sample we want to measure is being lofted into space where we can much more easily access it. The kicker here is we've looked for those plumes again and we haven't found them. And the Hubble observations a couple of years ago weren't the first time we've looked. We've looked with every spacecraft that has gone by Jupiter and have failed to find them. We looked again with Hubble with an even more comprehensive campaign, failed to find the plumes again. That's why it's a wild card. It's a high risk, high payoff situation. But these are the key, simple, straightforward questions that we need to answer in order to get at that big question, is Europa habitable? And as you can see here, other missions, other instruments have proven that we can answer those questions. So that takes us to where we are today. Through a lot of hard work, sustained hard work over the past decade, we were finally able to arrive at a mission concept that could address those questions for reasonable cost. The Europa Mission concept that was pitched to the Decadal Survey about 4 years ago, everybody thought, wow, this is great. The science is off the scale, as is the price tag. $5 billion is what Decadal Survey thought it would cost. And the response from the administration was, we don't care how great your science is, you're not getting $5 billion. Make it cheaper, which is exactly what Decadal Survey said to do. So in the time between then and now, what we were able to come up with was, instead of going into Europa orbit, instead of landing on Europa, the science definition team took a different approach. They ripped a page out of the Galileo playbook and asked the very simple question, instead of getting 10 or 12 flybys like Galileo did, what science do we get if we do dozens of flybys? And the answer came back quite a bit. In fact, it was estimated that we could capture about 80% of the Europa orbiter science with 45 flybys. And when you fold in the potential of an extended mission of getting another 100 to 150 flybys, you're talking about a lot of flybys in this body. So that's the mission that we've been putting forward to the administration for the past 9 months. The Europa Multiple Flyby Mission concept that will look at the ice shell and ocean, characterize it, see how thick it is, look at the composition of the surface, the geology of the surface, and very, very importantly, do some reconnaissance of the surface. Eventually, and by eventually I don't mean in a year or two after this mission launches, but eventually, whether it's in 50 years or 100 years, we're going to want to land on Europa. That's how we explore. We fly by, we orbit, we land, we rove. Or in Europa's case, we swim. We currently don't have the data sets of the surface of Europa to even pick out a landing site, to even design a lander that could survive the landing process. So the next mission there, this mission, has to provide those data sets. That's the reconnaissance. This is the mission concept that NASA has approved to go into formulation and beyond. This is the mission concept that is now the new, as Yvonne said, the newest mission in NASA's portfolio. This is the next Outer Planets flagship mission. We've been making a lot of progress. As you guys may have heard, a couple months ago, we also managed to finish the instrument selection process. So we actually now have our science team and our science payload for this next mission. We have 8 instruments, actually 9 instruments, an infrared spectrometer, which Carly's probably very familiar with, a very capable mass spectrometer that goes out to 1,000 Daltons, a dust analyzer, an ultraviolet spectrometer, a wide-angle camera that's actually a wide and narrow-angle camera, which is why it appears here as well, which will give us a map of Europa down to the 50-meter resolution, 50 meter per pixel resolution, for about 90% of the surface from a flyby mission, not an orbiter. Keep in mind right now the Galileo data set we have is about 250 meter per pixel resolution for about a quarter of the surface. This is a huge step forward. Ice penetrating radar and a thermal instrument and a magnetometer with Faraday cups. So all of these payload elements, all of these instruments are what we determined were necessary to get at those 5 small questions that help us address that main question of, is Europa habitable? And we actually went beyond what the science definition team recommended we select for this mission by making sure we had an ultraviolet spectrometer and a thermal imager. So our best estimate right now is, compared to the $5 billion Europa orbiter that we presented to the decadal survey, this $2 billion mission accomplishes better than 90% of the science of that orbiter because we included a few extra instruments. So we're getting almost the entire science at less than half the cost, which you can imagine was very well received in the building in which I work. So that's all I have to say about Europa. I'm happy to take any questions you guys have. Are you running for the bathroom or the microphone, Bill? Or lunch?
Those are all good options. No, I just had a quick question. So following some of what's been going on in Congress, I want to ask a headquarters question since you're up there. I've seen some speculation that going along with the Europa mission, there might be actually a new RNA line to do research of Europa and maybe Enceladus together. Can you comment on that at all?
Yeah, it's been discussed. You know, we had the Outer Planets Research Program that was split in two, with about 70% of it going to solar system workings in the restructuring, and about 30 of it going to the Cassini Data Analysis Program. The Cassini Data Analysis Program is not going away in 2017 when Cassini hits the atmosphere of Saturn. We're not going to repeat the Galileo mistake of ending the data analysis program 6 months after the mission ends. So CDAP will be going on for quite a while. We have had discussions about what the RNA needs are going to be as we ramp up for the Europa mission, and that will become apparent when the budget is released in February-ish.
Okay.
Doug Curry, University of Maryland. It's a historical question. I'm wondering what the comparison is between Europa and Enceladus, where Enceladus we do have the plumes, and we've known that for quite a while.
It's an interesting comparison, that's for sure. Enceladus, like the plumes on Europa, was a real wild card, a wake-up, really. I think, and we know in terms of similarities, we now are confident that Enceladus ocean at the bottom is in contact with silicate, just like Europa's, which is often overlooked in terms of its importance for the implications for life. I think the key difference here is really when it comes to lifetime. We are confident that this environment on Europa has been stable for almost the lifetime of the solar system. Enceladus, not so much. We understand the heating mechanism for Europa and how long-lived it would be, not so much Enceladus. And I think when we talk about the 3 different ingredients for life, the chemistry, the energy, the water, we always forget that 4th ingredient, which is shelter. You need a stable environment, a stable house, a stable shelter for those 3 ingredients to have an opportunity to do some amazing things.
Great. Thank you very much. Before we thank all of our speakers this morning,